Hello everyone, a warm welcome to the next session of Deep Learning Foundation course. How are you guys? I hope all of you are fine. Yeah. So in the previous session, I hope you have understand module 1, Introduction to Deep Learning. So I hope you remember in the previous session, we have seen introduction of deep learning. What is deep learning? Yeah. And then we have seen what is a neural network. Am I right? And then we have seen 3 reasons to go deep and your choice of deep network. And I also have shown you deep learning market. Yeah, the growth of deep learning nowadays in the market. How fast the growth of deep learning is happening nowadays. Yeah, what is the growth of deep learning market nowadays in the market? Yeah, so I hope you understand all these concepts that we have taken in our first session. Yeah, so now let's continue with today's session. So in this session, we will start the module 2 in which you will learn deep learning models. Okay, so now let me show you what you are going to learn in the module 2 of deep learning models. Okay, so the first thing you will understand is restricted Boltzmann machine. What is this? You will understand all the concept about it. And then you will understand deep belief network. And then convolutional neural network. And finally, recurrent neural network. Okay. So before going to proceed further, I hope you got a clear concept. You have understand the concept of deep learning that we have taken in our previous session. Yeah. So we have taken what is deep learning. Am I right? And we also have taken what is neural network. We also have understand neural network. Yeah. What is perceptron? Yeah. 3 reasons to go deep. Yeah. And your choice of deep network. Yeah. And then finally, I have shown you the deep learning market. Okay, how it is growing nowadays, how fast it is growing. Yeah, so now let's start with this session with the first point of restricted Boltzmann machine. So do you know this? So let me show you what is restricted Boltzmann machine. So see, Geoff Hinton at the University of Toronto was one of the first researchers to devise a breakthrough idea for training the deep networks. His approach led to the creation of the restricted Boltzmann machine, also known as RBM. RBM, restricted Boltzmann machine. Okay. Because of his pioneering work, he is often referred to as one of the fathers of deep learning. Yeah. Are you getting the point? So Geoff Hinton at the University of Toronto was one of the first researchers to devise a breakthrough idea for training the deep nets or deep network. His approach led to the creation of restricted Boltzmann machine, also known as RBM. Because of his pioneering work, he is often referred to as one of the fathers of deep learning. An RBM, restricted Boltzmann machine, is a shallow two-layer network. The first layer is known as the visible layer, and the second is called the hidden layer. Each node in the visible layer is connected to every node in the hidden layer. Okay. So restricted Boltzmann machine, it is a shallow two-layer network. Two-layer networks. So the first layer is visible layer and the second layer is hidden layer. Each node in the visible layer is connected to every other node in the hidden layer. Okay. So let me show you. The network is known as restricted as no two layers within the same layers are allowed to share a connection. So you can see here the structure for restricted Boltzmann machine. Yeah, can you see here? So as I told you, restricted Boltzmann machine is a shallow two-layer network. The first layer is known as visible layer and the second layer is known as hidden layer. So see here, it's a visible layer, it's a hidden layer. Okay. Okay. Each node in the visible layer is connected to every node in the hidden layer. Each node in the visible layer is connected to every node in the hidden layer. Can you see this one? Yeah. Each node of visible layer, each node in visible layer is connected to every node in the hidden layer. So see here. So the network, you might think why this network is known as restricted. So see, the network is known as restricted as no two layers within the same layers are allowed to share a connection. So you can see here the structure of restricted Boltzmann machine. Okay. So remember RBM structure. So it has only two layers, visible layer and the hidden layer. Okay. Each node in the visible layer is connected to every node in the hidden layer. Okay, that you can see here in the image. Okay. RBM is the mathematical equivalent of a two-way translator. A forward pass takes input and translates them into a set of numbers that encodes the input. A backward pass meanwhile takes this set of numbers and translate them back into reconstructed inputs. Are you getting the point? RBM is a mathematical equivalent of a two-way translator. A forward pass a forward pass takes input and translate them into a set of numbers that encodes the input. A backward pass meanwhile takes this set of numbers and translate them back into reconstructed inputs. A well-trained net performs backprop with a high degree of accuracy. In both steps, the weight and biases have a very important role. They allow the restricted Boltzmann machine to decipher the interrelationships among the input feature, and they also help the RBM decide which input features are the most important when detecting the patterns. Okay, so a well-trained network performs backpropagation with a high degree of accuracy. In both steps, the weight and biases have a very important role. They allow the RBM to decipher the interrelationship among the input feature, and they also help the RBM decide which input features are the most important when detecting the patterns. Okay. Through forward and backward passes, the RBM is trained to reconstruct the input with different weights and biases until the input and their constructions are as close as possible. Through the forward and backward passes, the RBM is trained to reconstruct the input with the different weight and biases until the inputs and their constructions are as close as possible. An interesting aspect of RBM is that data need not be labeled. Okay, so the interesting aspect of the RBM is you do not need to have the data to be labeled. Okay, so an interesting aspect of RBM is that data need not be labeled. This turned out to be very important for a real world data set like photos, videos, voices, and sensor data, all of which tend to be unlabeled. Okay. Instead of manually labeling data by human, RBM automatically sorts through data by properly adjusting the weight and biases, and RBM is able to extract the important features and reconstruct the input. Okay. An important note is that an RBM is actually making decisions about which input feature are important and how they should be combined to form pattern. In other words, an RBM is a part of a family of a feature extractor neural networks, which are all designed to recognize inherent patterns in the data. These nets or networks are also called autoencoders because in a way they have to encode their own structure. Are you getting the point? Yeah. So see here, as we as I told you that the important aspect of RBM is that the data need not to be labeled. Okay, so this turns out to be very important for a real world data set like photos, videos, sensors, sensor data, voices. Okay, so all of which tends to be unlabeled data. So instead of manually labeling the data by human, restricted Boltzmann machine automatically sorts through data by properly adjusting the weights and biases, and RBM is able to extract the important features and reconstruct the input. Okay, an important note is that an RBM is actually making the decision about which input features are important and how they should be combined to form the patterns. In other words, RBM is a part of family of feature extracted neural networks which are all designed to recognize inherent patterns in the data. So these networks are also called autoencoders because in a way they have to encode their own structures. Got the point? Yeah. One aspect that distinguishes RBM from other autoencoders is that it has two biases. The hidden bias helps the RBM produce the activation on the forward pass, while the visible layers biases help the RBM learn the reconstruction on the backward pass. Are you getting the point? Yeah. So one aspect that distinguishes RBM from other autoencoder is that it has two biases. The hidden bias helps the RBM produce the activation on the forward pass, while the visible layer biases helps the RBM learn the reconstructions on the backward pass. RBM is a stochastic neural network, which means that each neuron will have some random behavior when activated. There are two other layers of bias units, hidden bias and visible bias, in an RBM. So this is what makes the RBM different from autoencoders. You might think, what is the theory about autoencoders? So don't worry, I will also explain you autoencoders in our later sessions. Okay. So see, in order to understand the restricted Boltzmann machine in a better way, focus on this image. Okay, so see here. So it's a visible layer, hidden layer, and the activation function. Okay, so the input is there. Okay, and then what is this weight? Okay, and then the hidden layers, and then the activation function. Okay, so now let's understand this one. Okay, so focus on this image and let's see what is this, the detail about this one. Okay, so see. The above image shows the first step in training an RBM with multiple inputs. Can you see this one? There are multiple inputs. So what we are doing here, this image shows the training of restricted Boltzmann machine with multiple inputs. Okay. The inputs are multiplied by the weight and then added to the bias. Okay. So the first thing is inputs are multiplied with the weight and added with the bias. Okay, the inputs are multiplied by the weights and then added to the bias. By the way, I hope you remember in a previous session of module 1, introduction to deep learning, I hope you understand how does the perceptron works. Yeah, we have seen what are the steps involved in the working of perceptron. Yeah, do you remember? So the inputs are going to multiply with the weight and then all the multiplied weights are going to be, we need to do the sum for that. Okay, I remember. So there are 3 steps we have seen. Okay, if you forget it, you can just go back to the previous session and you can see how does the perceptron work. Okay, so see here also what is happening. The inputs multiply with the weight and then added to the bias. Okay, the result is then passed through a sigmoid activation function and the output determines if the hidden state get activated or not. Are you getting the point? So the first thing what is happening here? the image that I shown you is the first step in training the RBM with the multiple inputs. So these inputs are multiplied with the weights and then added to the bias. The result is then passed through a sigmoid activation function, and the output determines if the hidden states get activated or not. So focus on this again. Okay. So the inputs are multiplied with the weight. After that, they are added with the bias. All the multiplied values are added to the bias. Is it correct? See here. And then added to the bias. After that, the result is then passed through a sigmoid activation function. The result is passed through a sigmoid activation function. This one. Okay. And the output determine if the hidden state gets activated or not. Okay. So what the output is determining here? The output determined if the hidden state gets activated or not. Okay. So see, there are inputs. So you need to multiply the inputs with their weight. Okay. The first step here, you can see this one. The image shows the first step in training the RBM with the multiple inputs. So these inputs are multiplied by their weights. The inputs are multiplied by the weights and then added to the bias. And the result is then passed through a sigmoid function, and the output determine if the hidden state get activated or not. So focus here. Are you getting the point? Yeah. So the first thing, inputs are multiplied with the weight and added in a bias. Inputs are multiplied with the weight and then added to the bias, and that result is pass through a sigmoid activation function, and the output determine if the hidden state get activated or not. Okay. The weight will be a matrix with the number of input node as the number of rows and the number of hidden nodes as the number of columns. Weight will be a matrix with the number of input nodes as the number of rows and the number of hidden nodes as the number of columns. The first hidden node will receive the vector multiplication of the input multiplied by the first column of the weights before the corresponding bias term is added to it. Okay. And if you are wondering what is a sigmoid function, so here is a formula for it. So as we are saying that the input, first of all, you are supplying the input, yeah, to the visible layer. So these inputs are multiplied by the weights and then added to the bias. The result is then passed through a sigmoid activation function, and the output determined if the hidden state get activated or not. So as we are seeing here, the result is passed through a sigmoid function. So if you don't know the sigmoid function, so if you are wondering what is a sigmoid function, so here is a formula of sigmoid function. So s of x is equal to 1 divided by 1 plus e raised to minus x, which is equivalent to e to the power x divided by 1 plus e to the power x. So what is here? S of x is nothing but the sigmoid function, and e is nothing but the Euler's number. Okay, Euler's number. Got the point? So this image shows the first step in training an RBM. Okay, so the first thing is the inputs are multiplied with the weight and then added to the bias. The result is then passed through a sigmoid function, and the output determined if the hidden layers get activated or not. Output determined if the hidden state gets activated or not. Sorry, if the hidden state, okay. Output determined if the hidden state gets activated or not. Weights will be a matrix with the number of input node as the number of rows and the number of hidden node as the number of columns. Are you getting the point? So what is weight will be in the form of the matrix. Okay, so that matrix, I hope you know that matrix contains the rows and columns. Yeah. So weight will be in the form of matrix in which you are considering, you are putting the number of node as the number of rows. Okay, the number of input nodes as number of rows and number of hidden nodes as the number of columns. Okay. The first hidden node will receive the vector multiplication of the inputs multiplied by the first column of the weight before the corresponding bias term is added to it. Okay. And then if you're wondering what is the sigmoid function, so I have written the formula for you. Here you can see s of x is the sigmoid function and e is nothing but Euler's number. Okay. Now this image shows the reverse phase or reconstruction phase. It is similar to the first phase but in an opposite direction. So initially, how the image look like this one? Yeah, this image shows the first step in training the RBM. Yeah, the above image shows the first step in training the RBM with multiple inputs. Okay. Okay, can you see this one? The inputs are supplying here to the visible layer and then the hidden layer as then the activation function. How it's working? Yeah, the inputs are multiplied with the weights and added to the bias, and then the result is passed through the sigmoid function. Yeah, and the output and the hidden layer and the output determines the result is passed then through a sigmoid activation function, and the output determine if the hidden state gate activated or not. Okay. Now this image shows the reverse phase or reconstruction phase. So it is similar to the first pass but in an opposite direction. Can you see this one? Activation are the new input. Yeah, and then the visible layer. The biases are the new, reconstruction are the new output. Yeah, weights are same. Okay, so the first image that I shown you, this one, it shows the first step in training the RBM with multiple inputs, whereas this image show you reconstruction. This image shows the reverse phase or reconstruction phase. It is similar to the first phase. It is similar to the first pass, but in an opposite direction. Got the point? So finally, let's note down some important point about restricted Boltzmann machine. So see, RBM are neural network that belongs to energy-based model. It is probabilistic, unsupervised, generative deep machine learning algorithm. RBM's objective is to find the joint probability distribution that maximize the log likelihood function. RBM is an undirected and has only two layers. Input layer, you can say visible layer, and hidden layers. Okay. All the visible nodes are connected to all the hidden nodes. Yeah. RBM, it has two layers, visible layer or input layer and hidden layer. Okay, RBM has the two layers, visible layer and hidden layer, or you can say input layer and hidden layer. So it is also called as symmetrical bipartite graph. RBM nodes also make stochastic decision to decide either to be turned on or off. Yeah, because as per the working, can you see this one? Once the result is passed through the sigmoid function, the output determined if the hidden state get activated or not. Yeah, got it? So now I hope you understand restricted Boltzmann machine, the theory about it. Yeah. So tell me, who invented the concept of restricted Boltzmann machine? From where? The research. What is the name of that researcher? See here in the first slide only, we seen that Geoff Hinton at the University of Toronto was one of the first researchers to devise a breakthrough idea for training the deep networks. So Geoff Hinton was the one of the first researchers to devise the breakthrough idea for training the deep networks. His approach led to the creation of restricted Boltzmann machine. Okay. And then we have understand the RBM structure. It has two layers only, visible layer or hidden layer. Yeah. Okay. And we also have seen a well-trained network perform backpropagation with high degree of accuracy. In both steps, the weight and biases have a very important role. They allow the RBM to decipher the interrelationship among the input features, and they also help the RBM decide which input features are the most important when detecting the patterns. And then we have focused on the image that show us the first steps in training the restricted Boltzmann machine with multiple inputs. Yeah. So the inputs are multiplied with the weight and added to the bias. The result is then passed through the sigmoid function and the output determined if the hidden state get activated or not. And then we have focus on the next image that shows the reconstruction phase. So it is similar to the first pass, but in a opposite direction. Yeah. And then we have seen some important point about restricted Boltzmann machine. Okay, got it? So now let's proceed to the next network. Next point, deep belief network, DBN. Okay, just like the RBM, deep belief networks were also conceived by Geoff Hinton as an alternative to the backpropagation. Again, the famous researcher Geoff Hinton. Yeah. So just like the RBM, deep belief network were also considered by Geoff Hinton as an alternative to the backpropagation. Because of his accomplishment, he was hired for image recognition work at the Google, where a large-scale DBN project is currently believed to be in development. Okay, so because of his accomplishment, Geoff Hinton, because of his accomplishment, Geoff Hinton was hired for image recognition work at the Google, where a large-scale deep belief network project is currently believed to be in a development. The deep belief network is a neural network constructed from many layers of restricted Boltzmann machine. So I hope you understand restricted Boltzmann machine. So see, DBN, that is deep belief network, is a neural network constructed from many layers of restricted Boltzmann machine. So see, the schematic representation of a deep belief network is shown below. So see here, this is a schematic representation of deep belief network. Can you see this one? The input layer, the hidden layer 1, hidden layer 2, hidden layer 3, the output layer. Okay. This belongs to the RBM1 because restricted Boltzmann machine contain only the visible layer and the hidden layer, or you can say the input layer and the hidden layer. RBM1, RBM2, RBM3. The number of layers and the number of input, the number of layers and the number of units on each layer is the schema are only example. We do not require to have the same number of units on each hidden layer. So this is just a schematic representation of a deep belief network. Okay. So see here in a deep belief network, we have the input layer, and then in between the input layer and the output layer, we have the hidden layers. Okay. So the number of layers and the number of units on each layer in a schema are only examples. Okay, it's for example. So we do not require to have the same number of units on each hidden layer. Okay, so it is not necessary that you should have same number of units in each hidden layer. Okay. A deep belief network is a sophisticated type of generative neural network that uses an unsupervised machine learning models to produce the results. A deep belief network is similar in a structure to a multi-layer perception, but very different when it's come to a training. In fact, the difference in a training methods is the key factor that enables deep belief network to outperform their shallow counterparts. Okay, so DBN is a sophisticated type of generative neural network that uses the unsupervised machine learning models to produce the result. A DBN is similar to MLP, multi-layer perceptron, but it is very different when it's come to the part of training. So in fact, the difference in a training method is the key factor that enable deep belief network to outperform their shallow counterparts. Okay, a DBN can be visualized as a stack of RBM, where the hidden layer of one RBM is the visible layer of the RBM above it. So I have shown you the schematic representation of deep belief network. Okay, so a DBN can be visualized as a stack of RBM, where the hidden layer of one RBM is the visible layer of the RBM above it. Okay, a DBN is trained as follows. So it's important. See, what we are seeing here in the previous slide, I told you a DBM is similar in a structure to the multi-layer perceptron. But when it's come to the part of training, it's very different. So in fact, the difference in a training method is the key factor that enables deep belief network to outperform their shallow counterparts. So it's important for us to understand the training of DBN. How you can train a deep belief network. So see, a deep belief network is trained as follows. So see, the first step, the first RBM is trained to reconstruct its input as accurately as possible. Okay. The hidden layer of the first RBM is treated as the visible layer for the second. And the second RBM is trained using the output from the first RBM. This process is repeated until every layer in the network is trained. Okay. So again, as I told you, as we are seeing that a deep belief network can be visualized as a stack of RBM, where the hidden layer of one RBM is the visible layer of the RBM above it. So let me again show you the schematic representation of RBM. So see here. So it's look like the RBM1. See, for your understanding, I have created this one. Yeah, RBM1. So it's the input layer, or you can say the visible layer, hidden layer. For RBM2, this is the input layer or visible layer. This will be the hidden layer. Okay. So what we are showing for a DBN can be visualized as a stack of RBM. Okay, stack of RBM, where the hidden layer of one RBM is the visible layer of the RBM above it. So see, the visible layer and the hidden layer. So the hidden layer is the visible layer for the RBM2 here. Okay, are you getting the points? Deep belief network are visualized, can be visualized as a stack of RBM, where the hidden layer of one RBM is the visible layer of the RBM above it. So the hidden layer of the first, this RBM is the visible layer for the RBM above it. Yeah. So for this RBM2, what is the hidden layer? This one, hidden layer 2. But this hidden layer 2 will be the visible layer for the RBM above it. That is for RBM3. Yeah, are you getting the point? And for the RBM3, this hidden layer 2 will be the visible layer and this will be the hidden layer. Yeah. So deep belief network can be visualized as a stack of RBM. Where the hidden layer of one RBM is the visible layer of the RBM above it. Now, what are the steps for training the RBM? So see, a deep belief network is trained as follows. So see, what are the steps for training the DBN? We have seen RBM. Yeah. Now, a DBN is trained as follows. The first thing is the RBM is trained to reconstruct its input as accurately as possible. Okay, so the first of all, RBM is trained to reconstruct its input as accurately as possible. The hidden layer of the first RBM is treated as the visible layer of the second, and Second RBM is trained using the output from the first RBM. And this process is repeated until every layer in the network is trained. Got it? Yeah. So how the deep belief network is trained? Got it? Yeah, in just 3 steps. Yeah. So this is the third step. An important note about a deep belief network is that each RBM layer learns the entire input. In other kinds of models, like a convolutional networks, early layers detect simple pattern and later layers recombine them. Now you might think, what is the convolutional network? So don't worry, the next topic, the next point we are going to discuss convolutional network. Okay. An important note about a deep belief network is that each RBM layer learns the entire input. In other kinds of models like a convolutional network, early layers detect simple pattern and later layers recombine them. Like in our facial recognition example, the early layers would detect edges in the image and the later layers would use these results to form the facial features. A deep belief network works globally by fine-tuning the entire input in a succession as the model slowly improves like a camera lens slowly focusing a picture. A stack of RBMs outperform a single RBM as a multi-layer perceptron outperform MLP outperform as a single perceptron. A stack of RBM outperforms a single RBM as a multi-layer perceptron. MLP outperforms a single perceptron. Okay. After this initial training, the RBM have created a model that can detect inherent patterns in the data. But we still don't know how exactly what the patterns are called. So to finish the training, we need to introduce the labels to the pattern and find out the network with supervised learning. To do this, you need a very small set of labeled sample so that the feature and the patterns can be associated with the name. The weights and the biases are altered slightly, resulting in a small change in the network perception of the patterns and often a small increase in the total accuracy. This set of labeled data can be very small when compared to the original data set. We saw that a DBN only needs a small label data set, which is important for real world application. Okay. The training process can also be completed in a reasonable amount of time through the use of graphics processing unit. Yeah. And the best of all, the resulting networks will be very accurate compared to a shallow network. So we can finally see that a DBN is a solution to the vanishing gradient problem. But what is vanishing gradient problem? So see here, for you I have written it. A problem with a training network with many layers, example deep neural network, is that the gradient diminishes dramatically as it is propagated backward through the network. The error may be so small by the time it reaches the layers close to the input of the model that it may have very little effect. As such, this problem is referred to as the vanishing gradient problem. Okay, so a deep belief network is a solution to the vanishing gradient problem. Okay, got the point? Yes. Now let's see the application of deep belief network. So the first application of deep belief network is a image recognition. Deep belief network can be used in a image recognition. A picture would be the input and the category the output. This technology has broad application ranging from relatively simple tasks like photo organization to a critical functions like medical diagnosis. For example, smart microscopes that can perform image recognition could be used to classify pathogens. This would elevate the reliance on rare specialists during the serious epidemics, reducing the response time. The next application is in a video recognition. Video recognition also uses deep belief networks. Video recognition works similar to a vision in that it finds meaning in the video data. For example, it can identify an object or a gesture of a person. It can be used in a many different fields such as home automation, security, and healthcare. Yeah. Now the next application of deep belief network is in motion capture data. Motion capture data involves tracking the movement of the objects or people and also uses the deep belief network. Got the point? Yeah. So now I hope you have understand restricted Boltzmann machine, deep belief network. Okay. I hope you understand how the restricted Boltzmann machine look like, how the schematic representation of deep belief network look like. Yeah. What are the steps for training the deep belief networks? Yeah. How it work? Yeah. And we also have seen that deep belief network, you can visualize deep belief network as a stack of RBM. A deep belief network can be visualized as a stack of RBM where the hidden layers of one RBM is a visible layer of the RBM above it. Yeah, got it? So now what I will do, I will continue with the next point of a convolutional network in the next session. But as of now, I hope you understand restricted Boltzmann machine. So who is the researcher? Tell me, Geoff Hinton. Yeah. And what about the deep belief network? Who is the researcher for a deep belief network? Tell me. Again, Geoff Hinton. Just like the RBM, deep belief network were also considered by Geoff Hinton as an alternative to the backpropagation. And because of his accomplishment, he was hired for a image recognition work at the Google, where a large-scale deep belief network project is currently believed to be in a development. Okay. And then we have seen how you can train a DBN and the application of deep belief networks. So it is in a image recognition, it is in a voice recognition, video recognition, motion capture data. Yeah. And we also have seen a deep belief network is providing a solution to the vanishing gradient problem. Okay. So I will continue with the next point of convolutional network in the next session. Okay. Yeah.